Hi, welcome back. So as we've seen now, the impulse response completely characterizes linear time invariant systems. There's another way of characterizing these systems using differential equations for continuous time systems and difference equations for discrete time systems. And sometimes using these equations is more convenient than using the impulse response to express the system. So let's have a look at how differential and difference equations can be applied to describe some linear time invariant systems. Now, as an example, take a free body force diagram of a car traveling horizontally to the right. So this car would be experiencing a normal force up, N. It has a weight down, W. If it's moving to the right, we'll say it has a drag force, or a frictional force that's proportional to velocity. So this rho, and that's a rho, not a p. That rho is a constant. It's the constant of proportionality. And then there's an applied force F applied from the engine. Okay, so that's the free body force diagram for this car. And we're going to assume the input of this system is the force F from the engine, and the output is the velocity of the car. So we're interested in how is the velocity going to respond to the applied force F. Now, first of all, let's just get some formalities out of the way. Newton's law says that, of course, the sum of the forces in the y direction equals mass times acceleration in the y direction, and the car is not accelerating in the y direction, and so the normal force and the weight cancel out, and so we don't have to worry about the y direction. We're going to be interested in the x direction. So the sum of the forces in the x direction is equal to, well, we'll take the right to be positive, so we have F, and then minus rho v, and that's equal to mass times acceleration in the x direction, like this. And if I rewrite this using notation that we use in the course, F will say F is the input, so we'll write that as x of t. Okay, minus rho, which is a constant. V is the output. That's what we are interested in. What is the response of the car? So we'll write that as y of t equals mass times acceleration. Well, acceleration in the x direction is the time derivative of velocity in the x direction, right? And velocity is the output. So the acceleration is the derivative of the output. Like this. Okay, so this is a dynamics example, but circuit examples would be similar. We have capacitors that respond to derivatives of voltages and currents. Inductors do the same. Resistors are proportional, and so we can set up a differential equation as well. So here is our differential equation. Okay, this is a continuous time system, so we have a differential equation that is describing this system. Okay, and I want to point out this is a linear constant coefficient first order differential equation. All right, let's try to understand. That's a mouthful, but let's understand that. First of all, it's a linear because none of the derivatives multiply any other derivatives. So it's linear because dy dt is not multiplying dx dt, or we don't have any of those mixing of derivatives. So that's a linear equation. It's constant coefficient because the constants in front of x, y, and dy dt are constant. So we have a 1 here, we have a rho here, we have a mass here. Those things, 1, rho, mass, they do not depend on time, so they're constant. And this is a first order differential equation because the order of the derivative of the output is 1, right? We have a first order or first derivative of the output. We can certainly have a second or a third, and we look at the output. So but this is a first order differential equation. Okay, so it turns out that linear constant coefficient differential equations can model linear time-invariant systems. Now, here's our differential equation. We might ask, how is the car going to respond if I put in some x of t? So here's t, and for argument's sake, we'll just say, maybe I'm not stepping on the gas pedal, and then all of a sudden I quickly step on it like this, and this is my input, so this is the force from the engine. All right, but the key here though is you have to understand that the force was 0. It has to be at 0 at some point. At some point I apply the force, so we're making that point t equals 0. That's when I apply the force. Okay, that's going to be important in a second. So I'm not going to go through how to solve this differential equation with you. That is prerequisite math. Okay, it does involve finding a particular solution and a homogeneous solution and adding them together and applying a boundary condition or an initial condition. So let's talk about that initial condition. Okay, but I guess before that we should just, let's be concrete here. I've got this equation, and now I'm giving you an input, and we can solve this equation for the output y. So that's exactly, what we've been doing. We have a system, LTI system, and I put an x of t, and I want to know, what do I get out? Right? So this differential equation, a linear constant coefficient differential equation, can characterize the system, just like the impulse response can characterize the system. Now, let's go to this initial condition. You should know from differential equations that the differential equation is telling you how the system changes or how it evolves. Okay? So it's not enough, though, just to know how the system changes. We also need to know how the system started, and that's the initial condition. So we have to impose a constraint, or we have to impose an auxiliary condition, because this is not enough to solve the entire equation. So usually we assume in signals and systems that the system is causal. Okay? And if the system is causal, then I don't know what I get out yet because I haven't solved the differential equation, and I'm not going to. But if the system is causal, the output cannot become non-zero until the input becomes non-zero. That was the idea behind causality. So if I'm not applying a force over here, then we're going to assume that the output is 0 over here, that the system is at a state of initial rest. And then now at t equals 0, when the force is applied, now something happens, right? I don't know what that plot looks like, but something happens there. So our initial condition in signals and systems is going to be that we assume the system is causal. So, to summarize so far, linear, time-invariant, causal systems can be expressed by diff EQs. Right. And not just any diff EQs, linear constant coefficient diff EQs. Now, this system I want to point out to you, we can illustrate as a block diagram. So if I take that equation and I solve for y, so I can add y to the other side, right, and divide by rho. So this would be 1 over rho times x of t minus m over rho dy dt. Okay, and I can draw a block diagram, and a block diagram would look like this. It's usually read left to right, so we have the input at the left. So the input comes in, then it gets scaled, so by 1 over rho, so that's a proportional block. And usually in block diagrams, we draw that as a triangle. For those of you who have taken electronics, this is an amplifier with gain 1 over rho. Okay, so x comes in, we amplify it by 1 over rho. Then we're going to add to that minus m over rho times the derivative, and when we do that, we would get y. Okay, so then we're going to take y and take its derivative. So this is a differential block. Right? Take its derivative. And then amplify by m over rho and add it back. Okay, so again, take a look at that. So x comes in, multiply it by 1 over rho, that's this term. Okay, then now we've got y over here, so we send y to a derivative block, so that's dy dt. Then multiply that derivative by negative m over rho, so that's this term. Add it back to this term, and that gives us y. So this differential equation is implemented by this block diagram. Okay, and again, those of you who have had analog electronics, this is an amplifier with gain 1 over rho. This is an inverting amplifier with gain negative m over rho, and this is a differentiator. And because the gain is negative here and it's being added back, or it's fed back, this is a negative feedback system. Okay, why is this important? Well, the inverse of this system would be a system that takes velocity as input and then the force from the engine as output. That would be the inverse, right? So you tell it what velocity you want or what speed you want, and then the output is the force to the engine. So what kind of system would that be? Yeah, that's cruise control, right? You tell it the speed, and then it outputs the force. So the inverse of this system is cruise control, and that will also be characterized by a differential equation, and that also has a block diagram. And so then now you can take this block diagram, and if you're well versed in electronics, you can start building a circuit that will implement cruise control. And this block here, this addition, that's from a summing amplifier. If you again, you can use analog electronics for summing amplifier. Op amps will do all of these things. Okay, so I'm going to erase some of this. And now I just want to generalize what we've seen here. This was a first order differential equation, linear constant coefficient. In general, we can have any order on the output. This is A. Sorry about that. This is A. This is D. This is the kth order derivative. on y equals k goes from 0 to m bk dk x of t. Okay. So this, in general, this is an nth order linear constant coefficient differential equation. So any linear time invariant system that's causal can be represented like this equation, where we have a sum of the various derivatives of the output with constant coefficients ak, and then that's equal to a sum of various derivatives of the input with constant coefficients bk. That's an nth order differential equation because the highest order on the output derivative is n. Okay, so I'm going to erase this. That was differential equations. Now let's look at the analogous procedure in discrete time. So that's the differential, or that's the difference equation, excuse me. Sorry. Okay, so we can have something similar. K goes from 0 to n, ak, y of n minus k equals k goes from 0 to m of bk x of n minus k. You see, because in discrete time, there's no such thing as the derivative. A derivative, as you should have learned in first semester calculus, is a limiting operation on a continuous plot. And so that does not make sense in discrete time. So in discrete time, we have differences. Okay, so here's our nth order difference equation. Okay, linear constant coefficient. The AKs are the coefficients in front of the delayed y's, and the BKs are the constant coefficients in front of the delayed x's. Okay, it turns out we can solve these equations in the same strategy, with the same strategy that you use to solve differential equations. That is, we can find particular solutions, we find homogeneous solutions, and then we add them together to find the total solution, and then we specify an auxiliary condition like initial rest or causality, and then we solve the equation. But we can also solve difference equations with recursion. We can leverage the fact that these are finitely sized time steps and use recursion to solve them. And so that's what I want to illustrate here with an example. So let's consider a first order equation y of n equals, y of n minus 1/2 y of n minus 1 equals xn. Okay, that's the difference equation that we're going to try to solve, and we're going to give it an input xn equals k, so some constant, times the impulse. K is a constant, possibly complex. Okay, we're going to try to find y. Okay, so first of all, notice that this equation is in this form. right? We have n is equal to 1, right? Because we have y of n minus 1. So it looks like k goes from 0 to 1. We have this is the k equals 0 term where there's no delay on y. And then this is the k equals 1 term where there's a delay of 1 unit. So that makes this negative 1/2. That makes a1. And there's a 1 in front of y. That's a0 equals. And then capital M is 0. There's no delay on x. And so that would make b0 a 1 here. So this is in this form. Okay. So the input is k times a delta function. Okay, this is x of n. And remember, the claim is that this difference equation is, hiding or characterizing a linear time invariant system. So we should be able to get the output then, given this input. This input becomes non-zero at n equals 0. So if we're going to assume causality, then y of n must be 0 for all n less than or equal to minus 1. The output cannot become non-zero before the input does. So the input becomes non-zero at 0, so all of these samples must be 0 at the output for it to be causal. So that's our initial condition. Now, suppose, and here's the recursive part of this. Suppose we want y of 0. Well, according to my difference equation, if I add this term over, y of 0 is x of 0 plus 1/2 y of negative 1. Okay, well, x of 0, here's x of n. X of 0 is k. And then 1/2 y of negative 1, well, we assume causality, so y of negative 1, right, is 0. So y of 0 is k. Okay, good. Notice we used a previous sample to calculate the current sample. We used y of negative 1 to calculate y of 0. Now let me calculate y of 1. Y of 1 is x of 1 plus 1/2 y of 0. Okay, well, x of 1, what is x of 1? Well, that is 0 plus 1/2 y of 0. Well, what's y of 0? Well, we just calculated that in the previous iteration. That was k. You see that? So this is the recursion part of this. We use what we calculate to calculate the next one. So what is y of 2? Well, that is x of 2 plus 1/2 y of 1. Okay, x of 2 is over here. That's 0. 1/2 y of 1. Y of 1 was 1/2 k. So this is 1/2 of 1/2 of k, 1/4 of k. Do you see a pattern? Well, I do. For n greater than or equal to 0, it looks like y of n, whatever number we plug in over here, is going to be 1/4 to the n, or not 1/4, 1/2 to the n times k. Let's see if that works. When n is 0, y of 0 is 1 times k. Yep. When n is 1, y of 1 is 1/2 times k. Yep. When n is 2, y of 2 is 1/4 times k. Yep. Okay, so this is our solution. And, that's part of the solution, and then the other part is over here. So what do we get out? We get out zeros until the origin. And then for n equals 0, we get out k. And then we get out half k, and a fourth k, and an eighth k, and 16th k, and so on. This is y of n. Okay, so hopefully you followed that. And one thing I do want to point out to you is that using recursion like we've done here, where you use the previous step to calculate the current step, this is perfect for a computer program, right? We could easily calculate these things in a for loop or a while loop, a loop in a computer program. And that's what I want to show you next, how to use a program to calculate these things recursively. And it's this type of analysis that's used in software signal processing. So if you have, some sort of application for your headphones where you increase the bass, or you increase the treble, or in control systems when you need to filter out something, what's happening behind the scenes actually is these types of programs that are solving or processing the signal recursively like this. So in the next video, we're going to take a look at how we can start to use a computer program to solve these things.